Hi everyone, it's me again, doing another, in this case we're going to be doing a pre-lecture video here. This is between the classes of Monday the 26th and Wednesday the 29th. Basically we're finishing up chapter 3 here in Harris. We spent a lot of time on Monday in our POGL assignment talking about the different types of error and how it affects data, so hopefully you all understand at this point that pretty much every measurement that you make is going to have some sort of error associated with it. And so the next step here you have to think about is, as you guys will see in a lot of your experiments in the lab, almost everything we do has multiple steps and multiple measurements. And so you can imagine things can get pretty complicated pretty fast because each measurement has some sort of error, right? And so if you're doing multiple measurements in the same to get the same piece of data, you're going to get multiple sources of error that are influencing your final value. And so section 3.4 in Harris deals with that, and we're going to go through and give you a little information on that and go through an example problem to sort of illustrate this. It relates directly to the lab we're doing on Tuesday. Okay, so there's basically two different ways that we will propagate error. One of which is through addition or subtraction processes, and so for example, in that case, we just basically square them and take the square root of the squared sums of them. So basically what we're trying to do is just negate any possible effects of there being a negative value. So we're always getting an increase here in terms of error. Or through a multiplication or division process where we use, in this case, we end up using the percent relative error. So what that is your error. Let's get rid of that. Try that again. So that's your error, your percent error equals your error divided by the value times 100. Okay. So basically, you're just taking the relative error of each point and then multiplying it, multiplying by 100, and then again, just like in a addition or subtraction process, you square them and sum them and then take the square root. And this will always, this will become a little more clear once we start showing you some examples. But again, I refer you to section 3.4 in Harris to look for some more information. There's some more practice problems. And in fact, I'm going to post a couple more practice problems up in on the Blackboard site. So yeah, so error always increases. All right, so if you're ever doing some propagation of error process and in the end you have less error than you began with, then something has gone horribly wrong. Okay, so just one sort of problem. So this practice problem deals directly with what we're doing in lab this week. We're making a secondary standard of sodium hydroxide that we're going to use to titrate KHP. And so how this works, we're going to measure out some primary standard here, and you're going to determine the moles of that, and then you're going to titrate that with sodium hydroxide, right? And so there's a couple things you want to note from this problem. One is that we're using weight by difference in order to weigh out the mass of the primary standard, and it's using a class 2 balance. Okay. I see this sort of little clues here, and the other thing we want to talk about is that the solution is being measured out by burette. Okay. And so this will become clear to you once we're in the lab what I'm talking about here and why these particular aspects are important. Okay. So if we think about this concentration, this is our final value here. This concentration is is moles per volume, right? And this is coming from the mass of KHP divided by the formal weight of KHP times the volume, right? That goes, if you look back at this problem, here's our mass, here's our formal weight, and here's our volume. Okay, and we're going to make a couple assumptions here, and one assumption is we're going to assume that the error from the molecular weight is very, very small, so we can ignore it. It's negligible. I cannot write here. Okay, and so so really our main sources of error are going to come from the mass and from the volume. So when you think about how we determine this, so for the mass, I said we did weigh by difference. You guys are going to see this in lab, that weigh by difference, that our mass is actually, we have an initial mass and a final mass. So the way this works, you have your final mass and your initial mass. This is what is used to determine your mass. Okay, and so this is, so you can see right here, so we basically have two mass measurements, and so this would be an addition, a subtraction process. Right? And the volume is a similar thing. So we're doing a burette. If you think about a burette, how one reads a burette, you read sort of an initial volume position, and then you empty out some of your solution, and then you read a final volume. So much like the mass, the volume is actually come from two measurements. So let's call this volume equals, again, we're going to have a V initial, that's V, oops, okay, V final. That makes sense, okay? And then we're going to end up multiplying or dividing here, right? And so we're going to have some error associated with the mass and some error associated with the volume, and then we're going to have to combine them together at the end, okay? So we're going to take this in a couple separate parts here. And so for reference, you want to look at chapter 2. Again, it's from your book, chapter 2, right, where it has some of these values. And I say in this problem that, right, if we look back here, I have a class 2 balance for the mass, right? And then our sodium hydroxide is measured via burette, right? And so if we're looking at a burette, let's just start with the balance. So we're doing a class 2 balance, okay? And we're looking on the order of, which one are we going to do here? So our tolerance is, since we're measuring out 0.65 grams, I guess I should mention here that we're using a 10-gram balance, okay? And so our error here, the tolerance here is 0.074. And so, if we want to determine this error here, what we have is an initial and a final, right? So that's a multiplication addition process. And so the error of our from mass. Again, if we look back at our formulas for an addition and subtraction process, right? We take the errors of the individual components, square them, add them together, and then take the square root. So in this case, our individual components are from an initial mass and a final mass, and these are both taken on the same instrument. So we're basically getting 2 times this error. So what we have is square root of our error associated with the initial squared plus the error associated with the final. So hopefully you can read that. And so if we plug in the value here, E mass equals, in this case, from our table, we see that there's 0.074 for both of them. And so 0.074, and this is in milligrams, okay, so be careful there, right? So 0.074 milligrams, right, is 7.4 times 10 to the minus 5 grams squared plus another, right, so this is now from the final because we do this twice, 7.4 times 10 to the minus 5 grams squared. Right. If you go through to that calculation, you end up with your error associated with your mass equals, ends up being approximately, we end up getting 0.0001 grams. Alright, so what I did here is I just rounded, okay. It's not real practical to go beyond 1 digit. So our actual mass, we went through and we said our mass was, right, 0.6500 grams. So our actual mass is, with the error, equals 0.6500 grams plus or minus 0.0001 grams. Okay, so this sort of tells you the confidence we have in our mass value. Okay, I'm gonna insert a new slide here. All right, so now we want to do the same thing but with the volume. So here we go. So our volume again is a burette reading. If you look at our burettes, what we're measuring at, we've got 31.83 milliliters, and so what we're looking at is a burette value of, we're probably using a 50 milliliter burette, okay? And so our tolerance is 0.05 milliliters, okay? And just like our mass, we have an initial and final measure here, so we're doing this twice, and this is the exact same thing, okay? So our error associated with the volume, error for volume, we'll call this E volume, is equal to, right, again, so now we have our error of our initial volume squared plus the error for final volume, squared. Okay, so if that makes sense to you. Let's see. I'll do it again. So error for volume equals error for volume from the initial reading squared plus the error of the volume for our final reading squared as well. Okay, and so in this case, in both cases, right, we're looking at milliliters, and we're looking at 0.05 milliliters. Okay, so if we go through this, oops, so our error associated with the volume is going to be 0.05 milliliters squared plus 0.05 milliliters squared. Right. So you go through this to calculation, you solve for error associated with your volume. That's going to be 0.07 milliliters. Okay. So so now we found, so if you want to find your actual volume, right, your volume is 31.83 milliliters, right? If you look back here, right, that's 31.83 milliliters down here. And this is actually, if we include our error, that's plus or minus 0.07 milliliters. Okay. All right, so finally, this is where things get a little more complicated. So what we're going to do is put these together, okay? So now we have, if you look back at our original equation, that, right, we have error associated with our mass and error associated with our volume, right? And if we look at this process that we're doing here, this is a division process, and so we have to follow these rules here, and we have to use percent errors, right? So we're going to, in this case, what we're going to be looking at here, so our percent error for our molarity is equal to our percent error from the mass plus our percent error from the volume. Okay. And if you remember, way back when I started this, right, technically we would also have a percent error from our molecular weight, but I said we're going to make this assumption and that's a negligible error, and they actually go through that in Harrison chapter 3.4 and 3.5 and look at the error associated with molecular weight, and you'll see that it is very negligible. So, okay. So in order to do this, we need to determine our percent errors, right? And so if we go back and we look and we see that, so percent error for our mass, right, is just our error or mass divided by the mass times 100. Right? So we go back and we look here, right? Our error is 0.001 grams, and our mass is 0.6500 grams, and so if we plug that in, we get 0.001 grams divided by 0.6500 grams times 100. This is a percentage, and so that ends up being, let's put this here. All right, and that ends up being, so we get 0.016%. Okay. I did that thing where I put the last digit here down, the significant figures. All right, and so if we also we can do the same thing for the volume. Right. In this case, I'm just going to plug the values right in. All right. So this is going to equal. In this case, we have 0.07 milliliters, which we calculated before, divided by 31.83 milliliters times 100. This ends up being about 0.2%. So you can see just from looking at these two that the error associated with the math is 0.016%, which is about 10 times less than the error from the volume. So you can see the major source of the error here is from this volume. All right, so we'll find this overall error is, right, square these and take the square root, so you get 0.016% squared plus 0.2% squared. Okay, so if we combine these two together, we determine our overall percent error. So our overall percent error for the molarity is basically 0.2%. Okay. So you can see that, right, our overall percent error is basically the same as our percent error from our volume. So that basically dominates and contributes all the error to our system, to our final value for concentration. And so if we go through, if you went through the calculation to determine your molarity, so you guys can see, I have another slide here. Where are we going here? Another slide. All right. So if our molarity ends up being, if we went through and we did our calculation, we determined that our molarity was 1.01100 molar. Okay. So it's our concentration, and so if we want to determine what the error is, we just multiply it by our percent error. Okay. And so our percent error for the molarity equals 0.2%. And you remember that is equivalent to the error associated with molarity divided by the molarity, right? In this case, times 100, right? So this is equal to the error associated with molarity times 0.1000 molar, which is our molarity times 100. If we go through, right, we solve for this, our error ends up being 0.0001%. 0.02 molar. Okay, and so our final molarity would be 0.1000 molar plus or minus 0.0002 molar. Okay. All right, so hopefully that shows you. So that was a lot of steps, but I want to give you sort of a complicated practice problem that would involve all the types of error. So again, right, we use that to determine the error in this concentration. Okay, and so if you'd like some more review, again, I recommend looking for chapter 3.4 in Harris, and also going through some of the practice problems that are going to be posted online. Okay, so see you in class.